Stella, how do we do this? Okay, is it a trig function? Is it a product rule? Is it a power function? Is it a quotient rule? Like, how do we do the derivative of y squared?
Power rule.
Okay, so multiply by the power, lower the power, and then do the derivative of the stuff inside with respect to t. So how is y changing over time? There's a notation we have for that. How is y changing with respect to time? And over here, same deal. Multiply by the power, lower the power, and then how is x changing over time? And then the derivative of a constant, how is the constant changing over time? Well, it's constant, it doesn't change. So, this is implicit differentiation applied to time, I guess. Related rates are, I'm gonna change everything, and check to see how it's moving over time. That's all I was asking you to do, was dy dt, dx dt. And as I said in, optimization, single variable calculus. Here, we have lots of variables. We're still a single variable calculus. This just means I need to tell you everything. I need to tell you dy dt and dx dt and x. I need to make it so that you have just one unknown. All right. We're gonna try an experiment. And if you wanna come work with these guys, so you're not solo. All right, so you guys have one of these at your table, and we're gonna make the bottom left corner the origin, so disregard the stuff. Yeah, so scribes, that's Julia, Claudia, Cameron, Alex, Roman, Adrian, Mayanne, Amelia. Julia's joined your group, so she's the scribe for you guys. Ola and so you guys are gonna do the drawing on the board. Recorders, you need to get a piece of paper out and write some stuff down. And speaker, I'll be asking you what we're doing. All right. Let's see. How many blocks are between here and there? Okay. We're gonna say car A. So reporter, car A starts at 17 blocks from this origin. So the scenario here is we have a car approaching a right angled intersection, and then there's another car, I don't know, maybe it's a cop car and a bad guy car. Bad guy car. It's gonna start 3 blocks from the intersection. Let's see, feel the power. Naomi, how fast is our A car going? Is it going 1 block per thing, 2 or 3? Which one? Pick one.
2.
We'll call it seconds. So car A is going this way at 2 blocks per second. We've got it as it is for the moment. Kyle, car B, how fast is car B moving?
1 block per second.
1 block per second, okay. So, recorders, I want some data. So, I said car A starts at, maybe I should call them A and B. Car A starts at 17. And we're having car B start at 3. So measure how far, like take the ruler and actually measure accurately to how many centimeters? Because
17 centimeters.
each block is 1 centimeter, right?
Wait, so we're making it back, it's not making sense. No, it totally, like, 17. The ruler doesn't lie. At 17.
Okay, well, how many is this one then? So look, it does, 0 isn't at the edge of the thing, it's a little bit, so. Over there.
17 and a half.
Oh, no, like the, yeah, I'm gonna like, I'll put the table.
Okay, we're having some issues measuring, what are you guys getting? 17.1? The only one is just
Oh.
now you have millimeters.
Thank you.
17.1, 17.3, it kind of matters, but, Franco, what'd your group get?
17.2.
Oh, okay.
Franco, what's the heck? You just said 17.
No.
So there's some debate about that. Okay, so in 1 time unit, where is car A gonna be? It's moving 2 blocks per second, so Franco said. Yes? And in 1 time unit, where is car B gonna be? 4. Okay, sorry, I should have specified, car B is running away. So measure again. So keep going till you run out of space. And record the distances between, like record the hypotenuse for me.
Okay. So this guy's at 15. And this other guy is at 4, right? Like, at least not really bad. 15.7.
Yeah.
He's at 5, like 13.9.
No, it's just going down.
14.
Where does it say he's being chased?
He is being chased.
So he's about to take like a left turn.
Yeah.
2. Okay.
So it's like the 3rd and 4th problem we're gonna do today, if time permits. That the cop car is approaching the intersection.
Oh,
Has
that's
got
not
to hang
bad.
a left to catch the bad guy car that's already turned the corner. And he goes screaming away. Or does he?
Oh, or sorry,
Because Kyle may go slow. Maybe he's got a flat tire, that's why he can only move 1 block.
11.
So, Sadie, what did you guys get as a measure for number 5? For 15 units? 15.5?
It's this one, the one.
12.1.
Eddie?
Yeah, it's over.
And then
18.6. Evan, what did you guys get for this one?
Yeah.
15.9? Okay. They're starting to diverge a bit. And guys, using the ruler, please realize that there is like an edge to it, that the edge is not 0, it's 2 millimeters in. Franco, what'd you guys get for here?
15.9.
15.9.
That's
Wow.
45.
For me.
Roman, what'd you guys get for the 13? You didn't get that yet?
Okay.
The next one.
13 and 5.
14.
14, flat?
Yep.
Nathaniel, what'd you guys get for this one? The 13? 13.6? Kari, what'd you guys get for the one that's 13 and 5?
13.9.
13.9? Naomi, what'd you guys get for the one that's 13 and 5?
Original point was
12.
$17.5.
This one? 14.1? Wow, guys. These boards are all uniform.
Yeah, there's 10.5 and 10.
Like,
And it's
that's off by half a block.
10.5.
Like, whatever you guys are measuring is off by a lot, and they're supposed to all be the same. Cameron, your group, what'd you get for the one that's 13 and 5?
13 right here.
13.9?
No, for 11.
Oh, 11 and 6.
12.4.
Okay, 11 and 6, you get 12.4. Jason, what'd you guys get?
12.5.
Yeah, it's over.
Evan, what'd you guys get? 12.7? Ray, what'd you guys get? 13.
Oh, yeah, it's Thursday.
There's not everything rounds to a whole number. The 9 and 7, did anyone get that measurement yet? 11.9? 11.9? Katie, did you guys get 11.4? Abby?
Yeah, that's what I started off with.
11.5? Amelia?
10 point.
The last one? Anyone get that? 11.3?
11.5.
11.3, 11.5, okay. Okay, so, all right, here's the deal.
111.
So what you are doing is measuring that distance. So related rates. What is the relationship of this distance, and that distance? Is there some math operation that I can connect them together? Pythagorean theorem, okay. So a squared plus b squared equals c squared. In this situation, everything was moving. So over time, which we're randomly choosing seconds, I guess. So multiply by the power, lower the power. How is A changing over time? Plus 2b, how is B changing over time? Variables all over the place. And they're not gonna go away. There isn't a way to do a lot of stuff. So I needed to give you a lot of information. First of all, I'm gonna divide everybody by 2 because I can. Make it simpler. What did A start off as in my problem? 17. What did B start off in the problem? 3. And using Pythagorean theorem, because God knows your rulers are not accurate, 17 squared plus 3 squared 289 plus 9, 298, whatever that is, square rooted. So what I wanted to know is how is the distance between the cop car and the bad guy car, whatever these things are, how is that changing over time? I just need to solve for dCdt, and I have the ADT and dBdt. However, so what is the change in A over time? 2 per second. Is A getting bigger or smaller? Smaller, so is it positive 2 blocks or negative? Negative. There we go, negative. And this one, is it getting a longer distance or smaller distance? Longer, so it's a positive 1. So negative 34 plus 3. So the cop car is closing in on the bad guy car at whatever that rate is, negative 31 over square root of 298. So you can figure out, like, if you had 5 seconds to catch him or whatever, will he be caught in 5 seconds, 10 seconds, 20 seconds? How long does it take? You can calculate that out. What do you think? This is related rates. Frankel, we'll just go with, that just didn't go down well, like the water, not that this was distasteful, right?
Yeah, it's just, there's.
Yeah, okay, yeah.
How this would allow us to say like the car would catch in 5 seconds?
We need to do more stuff,
I just wanted.
but for what we need to do in here, this is all we need to do is, how is that line changing, okay? So I have, because these problems have a lot of words to them. Sorry, here, Hanson out. Hey, Adams, here, Hanson out. I have them printed for you. So related rates, first step is we're gonna do the derivative of everything, well, we need to set up the system, but doing the derivative of everything with respect to time. You guys can erase your little whiteboards. Everybody got one? Thank you. Okay. So can you finish the warm-up question? This is the same question from the warm-up. Find dy dt if I tell you now more information. Dx dt is 2 when x is 1. What is dy dt? Do I know x, y, and dx dt? Sort of. X is 1. Dx dt is 2. I don't know why. How do I find y? Plug it in. So, problem, we get a positive and a negative. and that's just what it is. So it depends on if we're in the top branch or the bottom branch of the hyperbola. What's the question? Did I do something wrong? It's like par for the course this week. So that's all this one is. This problem's on the worksheet. So you're blowing up a balloon, and if you see, like when you do the first puff of the balloon, it gets huge, real quick, right? The second puff, it's relatively like not as impressive. Is that because your lungs held much less air? No. What, Ray? Why is it not as impressive on the second puff?
The balloon's already bigger, so.
It takes more volume to cover to add an inch of air around the outside of the balloon. It's a lot more volume to get that outside thing. Okay. So in solving these problems, we need to read through the question. Air is being blown into a spherical balloon. They're never spherical, but we're assuming they are. So that the volume increases at a rate of 100 cubic centimeters per minute. How fast is the radius increasing when the diameter is 50? What information do I know? Flynn, what can I pull out of that?
The radius increasing volume and also the diameter.
Okay, so give me the variable name. You said you, the change in volume over time is 100 cubic centimeters. Is it getting bigger, Roman, or smaller? Bigger, so it's positive. Like, please make sure to ask yourself that. Is the thing I'm looking at getting bigger or smaller? Is the water draining from the tank, or is it raining and being added? And the only thing AP ever gives you in the way of formulas is volume formulas. So they'll tell you, well, of course you know the volume of a sphere is 4 thirds pi r cubed. Michael, what other information do I know?
You're gonna try to find the slope at the point, the diameter is 50 centimeters.
Okay. Diameter is 50, and so that makes radius what?
25.
25. And you said we are looking for how fast the radius is increasing. So as a variable, Nathaniel, what is that? DRDT. Okay. So there's all the things we were told, or that we could, they gave us diameter. Well, I know how to divide by 2. So Adrian, with all of that, how would you proceed?
Plug that into the volume.
What do I plug into the volume equation? Is volume 100?
No.
But I do need to use the volume equation. What, in a calculus class when we've just learned derivatives, do you think we should do with it? Yeah, with respect to what? Time or radius? Which one are we gonna do? In optimization, we did change in volume with respect to radius. Here, all of these things are asking about time, so I should do the derivative of everybody with respect to time. So how is volume changing over time? Okay, Stella, can you do this one? Can you do the derivative of this side with respect to time?
1 pi r squared dRdt.
Listing out all of these things of what you're looking for, that will help you solve the problem. Like, where you guys forget or make mistakes in this is that implicit differentiation at the end that Stella just did. And how is R changing with respect to time? If you forget that, you're going to not have the thing you're looking for in the problem, and that should stand out to you. That should be the hint. Okay, Kathy, what can I do now?
You can plug in 100 to the left side, and R is 25.
So all those things, okay. The RDT. It looks like radius is changing 1/25 pi. What are the units? What, Amelia? Radius is changing seconds? Centimeters per second. Right, Bill, is this making any sense? Okay. All right, questions on that? Yeah?
Why the seconds and not minutes?
Oh, you're right, minutes. Because I didn't reread the question because it was scrolled off the top. Thank you. Okay? Like I said, part of the course this week, police mix. Okay, so this is written on your sheet. The general idea for each of these, draw a picture so that, because sometimes it's not obvious how to connect the variables together. You'll be happy to know that a lot of them, it's Pythagorean theorem, your old friend. When did you guys learn Pythagorean theorem? Geometry? I think you learned it before that, according to the curriculum, it used to be introduced in 3rd grade. I don't know that you knew what squaring things was then, but, anyway. So, here's the process. Pull all the information out that they tell you, look for a way to connect things, do the derivative of everybody with respect to t, and then evaluate. Okay. This one. Just so you guys don't get some homework problems wrong, or that you don't back yourself into a corner on a test. This one, we're just asking you, do the derivative of everybody with respect to time. Try that with your group, see what you get. And scribe, write down your collective answer on the whiteboard, preferably not on the side that has a graph. Pass, it's over there somewhere. down on the whiteboard. Between the three of you at the table, somebody should have gotten something.
Y over 3 R here at CTA plus Y over 3 R
Yeah, just the. I don't know why it's.
Each on there.
Wait, so DVPT's
Oh.
Anybody on this side that doesn't have a graph?
Blood.
You're right. I just gave it to the.
Yeah, yeah, for us.
That's kind of smart. It's too
So, let's see.
Format is not. It's not.
Is that an R or a T?
Wait, wait. That's the T.
Seriously? Here.
It's just missing the left
You only
side.
need to relate
So,
them. You don't
missing
need
the left side of the, I have a lot like that R.
to relate the table, so you just need to relate
And is that an H? I mean, that's a pi.
Pi.
And then you get it. Do you keep the vibrator on the second part too? or not?
Okay, one group says this. Another group says.
It's just so messy. It's just disgusting. Especially my handwriting.
So, I'm seeing variations, let's see, are these the same? Let's see. 2/3 pi r h d r t t, 2/3 pi r h d r d t, plus pi over 3 r squared d h d t. Okay, yes. The big deal is that's a product, both things are changing, and you needed to do the stinking product rule with this. That we just did optimization where we were like, oh, we're gonna get the ratio of the radius to the height, and no. This one, unfortunately, I didn't give you any information, I was asking you to do the derivative of everybody. How is it changing? Oh, larger than life. All right, next problem to try. Hot air balloon is rising straight up from a level from a level field and is being tracked by a rangefinder. I do not know what a rangefinder is. It is 500 feet from the liftoff point. Is the rangefinder on the ground or in the air or what? Ground, because it says liftoff point. Does it sound like the rangefinder is moving? No, okay. So, I don't think you have a picture. Draw a picture. Label your rangefinder and how far away it is. At the moment the rangefinder's angle of elevation is pi over 4. Where do I label the pi over 4? Where? Near where the R is? Because angle of elevation is standing on the ground looking up. That's this one. The yellow one is angle of elevation. You're standing up going, oh yay, everything's happy and sunny. angle of depression is you're standing there and you're looking down and you're all depressed and sad. It used to be blue, it's now faded to purple or whatever, but. The angle is increasing at a rate of 0.14 radians per minute. What is that? As a variable, what are we gonna call it? Evan? D theta dt. And we're looking for how fast the balloon is rising at that moment. What are we gonna call that? Cameron? dH dt, dy dt, something like that? Sure. So label your picture with those things. Chose H, so there we go. Is there anything else we can figure out before we start trying to do some calculus?
H at the beginning.
What is H at the beginning?
Tangent of 45. It's just 500.
Ah, there we go. First was saying, do the tangent of, wait a second, it's pi over 4, it's isosceles, this is 502. Yes? Don't know that we need it, but it's good to know. That we were given d theta dt. What do you think my equation's gonna be? It's gonna be something with an angle in it.
500 tangent theta is equal to h.
So probably tangent. You could use the other ones, but the other ones need the hypotenuse. Is the hypotenuse changing in length as the hot air balloon goes up? Does the hypotenuse change? Yes. Does the distance from the rangefinder to the liftoff point change? No, like, I don't really know what a rangefinder is, but to me, I don't think it moves. I think it's a box, a unit that sits on the ground. So Evan says tangent of the angle is h over x. I'm gonna leave it as x first. But Evan said 500. He didn't keep the x. Is x changing? Like, we just discussed this. No, x is not changing, so that's fine. You can change, you can put 500 in for x because it's not moving. If it is moving, no. Sita, how do I do the derivative?
We do the derivative with n, which is, secant squared.
Yeah, it's been a minute, hasn't it?
Yeah. Is equal to dh.
Missing something. I'm doing the
Oh,
derivative.
times,
Okay, easy peasy, without a calculator. What is secant of theta? What is it?
Hypotenuse over x. Hypotenuse over x.
Hypotenuse over x, so what is the hypotenuse without a calculator? 500 root 2, 45, 45, 90 triangle, 1, 1 root 2. So if it's 7, 7, 7 root 2, okay, it's 500, 500, 500, 500 root 2. So secant is, what did we say again? 500 root 2 over 500, which is just root 2. Root 2 squared is 2. 500 times 2 is 1,000. 1,000 means move that over 3 decimal places. So how is the height changing? We got a calculator? No. 140, what per what? Feet per minute? Related rates, what do you think? Better than optimization, worse than optimization? Okay, I see one up, one down. They're both. Yeah. Okay, so the bell is about to ring. We'll start with this one on Wednesday. Those of you who are old enough, go vote.